Hello students, welcome back. Let us resume our discussion in section 2. This is going to be a short video, very short video about just one example. Fermat numbers. If the nth Fermat number Fn, which is defined as 2 to the 2 to the nth power plus 1 is prime, then 2 is not a primitive root of Fn. Well, okay, when n is equal to 1, then let's see. No, let's do it this way. So, okay, all right. Let's ask Mathematica to do the computation. So we calculated first 5 Fermat numbers through Mathematica. So when n is 1, 5, that's a prime number. N is 2, then 17, it's a prime number. N is 3, then 257, that 2 is a prime number. N is 4, then this number, and it turns out this is prime as well. N is 5, I don't think this is prime. Okay, true, 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 and then false. Okay, those are first 5 prime numbers. And can Mathematica handle 6th prime number in real time? Oh, okay, it did handle. I'm a little bit impressed. 7th? Okay, I'll stop here and look at the size of this number. God's sakes. So it's really hard to check and do any kind of computation with Fermat numbers. As you can see, numbers grow really quickly. And first 4 Fermat numbers are prime, but after that there is any more prime or not, actually nobody knows. As far as I know, it is still open, but who knows, there may have been some recent development. So in this case, f sub n is prime and n is greater than 1, then 2 is not a prime root. 2 is not primitive root of Fn. That's what you have to prove. Let's see. When n is 1, then f sub 1 is 5. In that case, I think 2 is a primitive root. Let's see. 2 to the first power is 2. 2 to the second power is 4. That's congruent to negative 1 mod 5. 2 to the third power is 8, so that's congruent to 3 mod 5. 2 to the fourth power is 16, that's congruent to 1 mod 5, right? Yeah, and then 2 to the p minus 1 power is 1, and that's the first one. So yes, 2 is indeed a primitive root of 5. So we have to start from n greater than 1. So for n greater than 1, 17 and 257, and then 65,537, and then beyond that, nobody knows. In any case, we have to prove that 2 is not a primitive root of Fn. Okay, I don't know what is the motivation of this. I do know those Fermat numbers are somehow related to geometry. whether you can draw a regular n-gon using the straight edge ruler and compasses only. But beyond that, I don't really know too much about the motivation of Fermat numbers, except for that conjecture that I told you about. As for this prime, okay, let's try. If n is 1, f1 is 5. In this case, 2 is a primitive root of f1. So we have to start from n greater than 1. In that case, let's use this factorization, 2 to the 2 to the n plus 1 power minus 1. And this is basically something square minus 1. So we can decompose as square plus square, square minus square. You see, this can be considered as 1 squared. And then 2 to the 2 to the n power plus 1. This one here is Fermat number. And this one is an integer, so Fermat number times an integer. So this is congruent to 0 modulo Fn. Make sense? And then consequently, this thing is congruent to 1 mod Fn. So 2 is 2 to the n plus first root of unity modulo Fn. That's what I'm getting. Therefore, the minimum should be less than or equal to that. Oh, excuse me. The minimum should be less than or equal to that. And this minimum is, of course, the order of 2 modulo Fn. Make sense? The smallest positive integer such that 2 to the k power is congruent to 1 modulo Fn. Okay, that's what you got so far. Therefore, the order of 2 modulo Fn cannot exceed 2 to the n plus first power. Yeah, that's what we got. The order is less than or equal to this. Now let's change a viewpoint. Because f sub n is prime and n is greater than 1, phi of fn is fn minus 1. And Fermat number is 2 to the 2 to the n power plus 1. So minus 1 again, we have 2 to the 2 to the n power. And that's far greater than 2 to the n power. So what is that? If 2 is a primitive root, then the order of 2 should be equal to phi of fn, but that's greater than the order of 2. So the order of 2 is strictly greater than itself. That's a contradiction. You see, the order if 2 is a primitive root of fn, then the order of a modulo m must be phi of fn. Yeah, that's the definition of the primitiveness. And then that's 2 to the 2 to the nth power, and that's strictly greater than 2 to the n plus first power. Oh, sorry about that. This one is much bigger, but then again, that's greater than or equal to the minimum of, let me copy and paste this thing here. Which is the order of a modulo m. Yeah, let's not use this minimum, because this minimum is nothing more than the order of a modulo m. let's use this back again. So what you have, the order of A modulo M is strictly greater than itself. That can't be right. There goes the contradiction. So this can't work. So we successfully proved that if the Fermat number is prime and n is greater than 1, so Fn is not 5, bigger, then 2 is not a primitive root of Fn. The problem is, what is the motivation of this problem? I don't know. And then also, what do you mean by this thing is prime other than those, for example, F1, F2, F3, and F4, and otherwise nobody knows. So I don't know about this. How important? I honestly don't know. I just did it because it appears in the textbook. Our textbook author may come back and pick up that for something else, or maybe not. In any case, we covered it, but I'm going to leave it as an optional topic, at least for now. I may later change my mind if that becomes important, but for now, I'll leave it as an optional topic.